السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last time we started to talk about convolutional neural networks. We talked about 1D convolution, and with the parameters that we have with it, which are the stride, the kernel size, and the dilation. And I think we stopped at that slide with these examples. So we talked about 1D convolution or 1D convolutional kernel, which is a vector of weights, and these weights are applied to a specific region of the input. We computed the weighted average of the values of the input, and that will be one value on the output, and that kernel is shifted by the value of the stride over the 1D input. And we also mentioned that at the corners, there are special cases when the kernel is, for example, when the kernel is centered at that point, then we have two options. One is to add zeros, which we call it zero padding, or we can restrict the application of the kernel to only valid convolutions. In that case, we will not produce, we will not apply the kernel centered at x1, but we will start applying the kernel centered at x2 and so on. So we will not have ones at the corner. And we talked about the stride and the kernel size and the dilation. And if you remember the examples here, this is a kernel of size 3 applied to the regions of the input. This is the same kernel, this in applying this kernel, we have a stride of 2 because we have here values that are not computed, right? So we actually shift the kernel here by a value of 2. So the stride here is 2, and then for the next step, so initially we centered it at x1. Here it is centered at x3 because the stride is still 2. For that example, we have a kernel of size 5. So we have 5 weights. It is applied at a region of 5 values. And the stride here is 1, right? How can we tell if the stride is 1 or 2 here? Yeah, the shift. So you see that the output values are almost the same, like in terms of number, like the values in the input. So that means that the kernel is shifted by 1. In the last example, we can see that the kernel is applied at a region of 5 values in the input, but we have only 3 weights. So the kernel size is 3 here, but the dilation is 1 because we are skipping 1 value in between each pair of weights. And I think this is exactly where we stopped last time. Now, after we discussed what we mean by 1D convolutional kernel, let's now talk about convolutional layers. Okay, how can we have a layer out of the kernels? The idea is very simple, and we are very familiar with it. We will apply the kernel to the input, to a region of the input. We add a bias. Applying the kernel means what? Means the weighted sum, right? We will compute the weighted sum, add the bias, and then apply the activation function. So exactly like what we do in standard neural networks, right? So we will do the weighted sum, add a bias, and then apply an activation function. And we do that over every region in the input. So in equations, you can see that this is the weighted average, applying the kernel centered at xi. Then we add the bias, then we apply the activation function, which is also commonly the radio function or any activation function. Okay, so that's now a layer that will produce one complete column of hidden units. Okay, now we can call them hidden units because they are very similar to the hidden units we talked about before. Right. This can be seen first before we compare it with the fully connected network. You can notice here that the computation of the hidden unit number I, we apply the kernel with W1, W2, W3, and the indices here have nothing to do with I, which means that the same kernel as we saw before, the same kernel would be applied to produce different hidden units. Okay, so it's the same set of parameters, same kernel will be shared across the entire input, and also the bias is independent of the hidden unit, so it's just one bias. So out of this operation or this layer, we only have 3 weights and 1 bias if we have just one kernel. Okay, so the entire layer is just has 4 parameters, 3 weights and 1 bias. Of course, if the kernel size is 3. Compare that to a fully connected network. You can see that it is a very special case of a fully connected network. In fully connected network, we have for each hidden layer, we have this equation, right? You saw it so many times before, right? The weighted sum plus the bias, applying it to the activation function. But here, the weights are different for every hidden unit. Okay, remember the hidden unit has incoming weights, and these weights are not shared across the different hidden units. So that's a big difference. So for one layer in a fully connected network, if we have D weights, D inputs, and D hidden units, then we will have these square weights between the input and the first hidden layer. If we have D here and D here, then the number of weights is D squared, right? Compare that with what we have in a convolutional layer. It doesn't actually depend on the number of inputs, right? It just depends on the size of the kernel. So the number of parameters here is much less than the number of parameters in a fully connected network, right? Okay, now let me show you an example. This is a fully connected layer. Okay, so we have an input, six inputs, and we have a hidden layer of 6 units. The number of units, the number of weights between these 2 layers is what? 6 times 6, right? 6 times 6, which is represented by the matrix down here. Okay, so this matrix, the colors here indicate the weights, the different weights. So we have 36 different weights for one fully connected layer, right? Now, this is an example of a convolutional layer. Applying a kernel of size, can you tell the size here? From that figure, can you tell the kernel size from that figure? So let's take this unit. This unit is a weighted sum from x2, x3, x4, right? And you can see h4 is still also a weighted sum of 3 nodes, and so on. So the kernel size here is 3. Okay, right. How about the stride? It's 1 because we are shifting, having the same size of the input. Okay, so its stride is 1. How about dilation? 0, because you can see that we are not skipping anything within the kernel. Okay, now this can be represented in the matrix here. So, for example, H3 is a weighted sum of x2, x3, x4. So H3. Okay, H3 is a weighted sum of x2, x3, and x4. Okay, H4 is a weighted sum of x3, x3, x4, x5. And notice that the colors here are exactly the same across rows, right? Why is that? Because it's the same kernel. It's the same kernel. Okay, so over all of this matrix, we only have 3 different weights, but they are repeated because we are applying the kernel to every region. While in the fully connected layer, all of these weights can be different. So we have 6 square here, we have just 3 weights here, plus the bias. Okay, so you can clearly see that the convolutional layer is a special case of the fully connected network, right? So you can think of it as a fully connected network, but most of the weights are zeros, and actually the weights also are similar across different hidden units. Okay, they are the same. So it's a very special case. Yes. Yeah, so here we are applying zero padding, right? How can we tell that? Because you can see that these are only 2, right? Although the kernel size is 3, and you can see that also from the matrix. Okay, it has only 2 weights, and the third one is not there, so the third one is 0. There are methods that rotate the input. Yes, it's a hyperparameter. You can try. Yeah, there's no single rule for that. Okay, so you can try zero padding, you can try valid convolutions. This is rotated convolutions. Yeah, it can happen. Right. Here's another example where what's the size here of the kernel? Why is it 2? 3, right? Look at the majority, because don't look at the corners. The corners they might be special cases, right? Okay, so don't look at the corners when you want to determine the kernel size. Okay, look at hidden units that are not at the corner. So that's 3. Okay, so it's the kernel size is 3. Are we? Do we have any dilation here? Are we skipping? No, we are not skipping. How about the stride? We are not skipping within applying. When we apply the kernel, we apply it to a region, all the values in a region, right? We are not skipping between the weights. Okay. How about the stride here? 1, because we shift 2 actually. We shift 2. So this one is centered at x1. This one is centered at x3. Okay, and this one is centered at x5. And how about padding? Do we have 0 padding here? Yes, we have 0 padding. How did you know? Because this has two values only, huh? and you can see that also here. Okay, this one has 2 only, which means that there is a 0 here for the non-existing elements. Okay, the stride here is 2 actually. Oh, it's written 1. No, it's 2. Okay, yeah. Any question about that? Again, this is a special case of a fully connected network, right? So a fully connected network in this case, how many weights we should have? And if we have input like that and hidden units like that, how many weights we will have? How many weights in between these 2 layers? 6 times 3, right? It's fully connected, so we have weights between all the nodes, right? So we would have 6 times 3, which is 18. Here we have how many weights? Just 3, because the kernel size is 3. Okay. Come on, we have only 1 bias here. Okay, in fully connected network, how many biases we will have? 3, because we have 3 hidden units, right? Okay. Is that clear? Okay. Right. Let me now ask. For this, what is the kernel size? What's the stride? What's the dilation? Do we have 0 padding or valid convolutions? Size is 5, right? Because we have 5 incoming weights here, and you can also tell from the matrix, right? From the matrix, it's clear size is 5. How about the stride? If you look at the matrix, can you tell what the stride is? Yes, how? Because we are shifting. You can look at the weights here. They are shifted with every row. We are shifted by 1, right? So the stride here is 1, right? Okay, and you can tell it also from the figure, right? From the network. How? Look at the exact weights. So H3 here is centered at X3, H4 is centered at X4, and so on. Right? Right. How about, so we talked about the dilation. Oh no. How about dilation? Are we skipping any? We are not, right? We are not skipping between the weights. We are not skipping any elements of the input, right? So dilation is 0. How about the zero padding versus valid convolution? Which one we are using here? The first one has only 3, right? So the remaining 2 are zeros. Same here. Now for this padding or valid convolutions, look at the corners, right? So the corner cases, here we have only 3 weights instead of 5, right? So the other ones are zeros. Yes, because it is the size here is 5, right? So it has to add also 0. Now these are considered now corner cases also. Yeah. Here we have 4. Here we have 3 also. Zero padding. Yeah, because in this case we will produce the same number of input units. Okay, if you want to keep the same size, then zero padding is the solution. It's special cases. You have to handle them somehow. Okay, because if you do the valid convolutions, what will happen to the size of the output? It will be reduced a little bit. Okay. Right. How about this? Think before you answer. The size is 3. Okay. Stride 1 or 2. The stride is about shifting the filter, right? The kernel, right? It's 1 here, right? You can tell from here. You can also tell even easier from here, right? How you can tell the stride from here? You can see that this is like the kernel, right? These are the weights of the kernel. You can see to compute H4, we shifted the kernel one element, right? One position. Okay, so the stride here is 1. How about dilation? Dilation? Here we are not skipping, right? So if you look at this, it is x3, x4, x5, right? That's the region. So we are not skipping any of the values. Are we doing valid convolutions or zero padding? How did you tell? Yeah, so you can see that every one here has 3 weights, right? Yeah, so 3 weights. It's only applied on valid inputs. We are not padding with zeros here. Okay. Any questions? How about this? Kernel size is 3 or 5? The region is 5. But the weights are 3, right? The weights are 3. So the size is 3. Stride 1 because we are shifting by 1. Dilation 1, and you can tell it very easily here, right? Yeah, these white cells are zeros. Okay, so there are missing elements here, right? So the dilation is 1, and are we doing zero padding or valid convolutions? Zero padding. Why? It's zero padding because you can see that this is 3 only, right? It's applied on the region of 3 instead of 5. Okay, any questions? Okay, now let's extend the idea a little bit to what we call channels. We are still in the convolution layer, by the way. Okay, but what we have covered so far will produce one channel in the layer. What do we mean by that? Or why do we need actual channels? Channels, as you will see, will be produced by multiple kernels. Each kernel will produce one channel in the layer. Okay, why do we need to apply multiple kernels? Applying one kernel only will make us lose some information. Okay, we are applying it to the same input, but it is just a very small number of weights that will learn one pattern. What if we want to learn multiple patterns from the same input? Okay, so we'll have to apply multiple kernels to the same input so that we can learn different patterns. طيب. We'll do that with applying several convolutions in parallel. Each convolution, each kernel will produce one channel in the layer. Does that remind you of something we discussed in transformers? In transformers. Do we apply something multiple times in parallel? Yes, but more importantly, the heads, multiple heads. So you can say attention, like the multi-head attention, right? Multi-head attention. Okay, because we want to get attention in different ways, different representations of attentions by applying multiple heads. Okay, this is a similar idea. Actually, this idea precedes the idea of transformers. CNNs are there before even transformers. Okay, so we will see now that we will apply multiple kernels in parallel and stack them in channels. We call them also feature maps. Let's see how this is done. This is one kernel, right, applied to the input, and that will produce a column of hidden units. Now we call this a channel. Okay, by applying one kernel to the input, we will produce one channel. Okay, right. Applying another kernel to the same input will produce another column of hidden units. We call that another channel. So now in the layer, this is in the same layer, we have two channels. This is channel number 1. This is channel number 2. Okay, so these are two channels within the same layer. So every kernel will produce its own channel. Notice that this kernel is different from that. Why I'm saying they are different? Because we have different weights. W1, W2, W3 here, W4, W5, W6. Of course, this is applied to the whole input, right? To all regions in the input. So this one will produce channel 1, which is this, and this one will produce another channel in the layer. Okay, with me so far? So this is one layer with two channels. Type. What if we apply the third kernel? We have a third channel in the layer. So one layer can have multiple channels. How do you know how many units in one hidden layer before? Okay, you got the idea now, right? It's a hyperparameter. Okay, you can change it. Right. In terms of parameters, how many parameters we will have now? Let's say that we have two channels in the output. How many parameters we will have? And 2 bytes. Yeah, it's number of parameters of one kernel times the number of kernels, right? The number of channels. If we have 2, then we will just multiply by 2, because each kernel now, if we have the size of 3, each kernel will have 3 weights, 1 bias. Okay, the second kernel will have 3 weights, 1 bias, right? So we'll have double. Yes. No, because channels of different sizes might that will not be consistent. They will, we'll have to have the channels of the same size. Okay, it will make processing much easier. Yeah. If not, then it will be very hard. Did I answer your question? Yeah. Okay. The number of channels is a hyperparameter. The size of the channel. The size of the channel is determined by the parameters that we talked about: the kernel size, the padding, the stride, the dilation, right? That will determine the size of that. But but the number of hidden units in each channel has to be the same. Okay. Mm-hmm. No, theoretically yes, but changing the stride might lead to different sizes of the channels, right? And we said that the channel size will be the same, so they have to have all the same kernel size, same stride, same everything, but different parameters, different weights and biases. Yes, it should be the same. Yes. Yeah, but now if we do that theoretically, yes, you can do that. But if you do that, then the meaning of or the how each kernel is computed will be different. Okay, so that's not done. But theoretically, yes, you can. Okay. Not very sure, to be honest. Okay. What I always see is that the kernel structure is the same across different channels. Okay. Question? Okay. So again, the number of kernels is the number of channels in the layer. Right. This is to create different output channels. Right. Can we have different or multiple input channels? Yes. Because remember, it's a neural network, right? A neural network is a stack of layers, right? So this can be we can stack another layer after this layer, which means that this layer now is an input to the upcoming layer. So the incoming layer can have multiple channels also. Let me show you an example. Here, the input layer, the incoming layer, has 2 channels. Okay. Now, to apply a kernel, it has to be applied to the same region across the input channels. Okay. So before we had just one input channel, right? Right. So we apply the kernel just to one region, to one channel. Now, when we have multiple input channels, the kernel will be applied to this region and that region, the same region across the different input channels. It's like the depth for the kernel. Okay, but of course with different weights. So now the number of weights will increase. So now this kernel is still of size 3, by the way, because for each channel we have 3 weights. But now we have 3 weights for this channel and 3 other weights for that channel. And all of them will produce just one hidden unit. Same weighted sum, and then one bias, and then the activation function. Okay? So before we had just one of these, right? We had just 3 weights. Now we will have 6 weights because we'll apply 3 to the first channel and 3 to the second channel at the same positions, but across different channels. Okay, so basically we will multiply W1 prime by H2 plus W2 prime by H3 plus W3 prime by H4 plus W4 prime times H8, W5 prime times H9, W6 prime times H10 plus the bias, and then we apply the activation function. That all will produce one hidden unit. Okay, and of course moving that kernel will produce not hidden layer now, it's one channel in the layer, because if we have another kernel, we'll have another channel in the same layer. Okay, so the layer now has channels. That's the convolutional layer now. Okay, so we can have multiple input channels and we can have also multiple output channels, and they are different. I mean, the processing, you have to understand that the processing is different. When we have multiple output channels, that means that we have multiple kernels. When we have multiple output channels, that means that we have multiple kernels. Each output channel is produced by one kernel. Okay? Now, this kernel will be applied to all input channels, to one region across all channels. Okay, one region across all channels. So even if we have 3 channels here, we will have 9 weights: 3 for the first, 3 for the second, 3 for the third channel, input channel. So it has like a depth. The kernel now has a depth because we have multiple input channels. Okay, question? Okay, yes. Yes, of course, multiple layers now. The very, very last, yeah, it depends on the test that you are doing. We'll see an example. We'll see an example today. Okay, yes. But you can, but you can see now that we can stack layers, right? Like before, right? But now the layers are convolutional. And you can see even that we can stack even fully connected layers. We'll see that inshallah today. Yes. Yeah. Say it again. Yes. These are hidden units in one layer. Okay. So here, because we have 2 kernels, we have 2 channels in the same layer. This is one layer. So this is one layer with 2 channels. Yes, each kernel will work in parallel, will process the input in parallel. Each one will produce one column of hidden units. We call it a channel. Okay, got your point. No, it's also a channel because we will move it also. This will move. This is a kernel. Kernel will always move across the entire input. You forgot that. Okay, so in this specific moment, it is applied to this region. So it will produce this unit, this value. But to produce this, what will happen? Yeah, we'll shift it. Okay? Yes. Oh, yeah. If this is everything, if this is everything, then this is we have one output layer, one output channel only, which is produced, of course, by one kernel. Yeah. Yes, of course. As we change the hidden units in the layers in a neural network, right? We can say, مثلا, this hidden unit has 10 nodes. The next one is 20. Third one is 5, right? So that's also the number of channels here. Yeah. Yes. Yes. That's why you have 2 output channels. I know that it might be confusing, but I'm trying to explain it, trying to be as simple as I can. Okay. So each kernel produce one complete output channel. Okay. And don't be fooled by the word output here. I mean, one output channel within the layer. It's not the very output, okay, the very last output. It's just one channel in the layer, okay? And each kernel will produce one input channel only, or all of them will process. Each kernel will process one input channel only, or all of the input channels. All of them. All of them. Each kernel will process all of them. Okay? Yes. Yes, 12 input values structured into channels. Yes. When we have 2 output channels, yes, as we increase the number of output channels, the parameters will increase or decrease. As we increase the number of output channels, the parameters will increase or not? Will increase, right? Will increase. Okay, just a second. You are confused. Okay. When if we fix everything except that we added or we have more input channels, okay, are we changing the number of parameters? Are we increasing? Are we reducing the number of parameters? Which one of these? Again, we have, let's say, 2 output channels, okay, and 2 cases of the input layer. One input, 1 channel only, and 2 channels, okay. The number of parameters of these 2 layers is the same or different? It's different, right? So it will increase when we have more input channels, right? Because of the depth, right? Because of the depth. Type. If we increase the number of output channels, it will increase, but because we are adding more kernels. Okay, so the reason is different. Okay, for the input, with the input, we're increasing the number of input channels, we are increasing the depth. So we have to add more weights to cover the depth. When we are increasing the output channels, we are adding more kernels, complete kernels. So with the weights and bias. Okay. But when we are adding more input channels, I should have poll questions for all of that, but didn't have time to prepare. But online questions now. When we add input channels, are we increasing the biases or they are the same? No. So we are not adding more biases, right? We are just adding weights, but it will be the same biases. Because we have the same kernels. We didn't add kernels. Yes. Say it again. Yes, of course. Yes, it is the same. The depth of the kernel is the same of the number of input channels, of course. So if we add a third input channel here, we'll have a third column of weights here. Okay, so it will be nine weights if we have three channels. If the kernel size is 3, if we increase the kernel size, then it has to increase across all channels. Okay, I hope it's not confusing now with all of this, with all of that discussion. Okay, so one kernel processes inputs from all channels at same positions. Okay, it's just depth, and this is one kernel of size 3. Now, how many parameters in general? If we have CI input channels and a kernel size of k, so how many parameters for that kernel? So we're talking about one kernel here. We have CI input channels and the kernel size k. How many parameters we have? CI multiplied by k. Okay, how many biases? 1. It's just one kernel here. Yeah, it's one output. Right? One bias because we have one kernel. Okay, one kernel. Okay, so we have CI times k. That's the matrix, the weight matrix. Okay, and one bias only. Type. If we have CI input channels and C out, CO or C naught output channels, how many weights we will have? Yeah, so all of that multiplied by CO, right? Because we have multiple kernels. So how many kernels we will have in this case? CO. Okay, so we multiply this by CO, multiply this by CO. So we'll have CI by CO by K. That's the weight matrix, would be 3D in this case. And the biases will be CO. No, of course you can. Plus knowing that it's a kernel size of K. Yeah, sure. Yes. Okay, any questions about that? Is that clear? Everything is clear? Okay. Now, another step. or another concept actually. It's not an extension of the convolutions, but it's another concept which is very important called the receptive field. Receptive field. What do you mean by receptive field? Very simple. The receptive field of any hidden unit. What do you mean by hidden unit first? No, one hidden unit is like one hidden unit, like what we discussed before, right? In the whole semester, it's just one unit in the layer, right? So a receptive field of a hidden unit is the region of the original input that feeds into it. What do you mean by feeds into it? That affects the computation of that hidden unit. Okay, so for example, first, before we talk about receptive field here, can we tell why we have these numbers? Can we tell the meaning of these numbers? One input channel, three output channels, and the size of the kernel is 3, right? Type. Why do we have three channels here? Because there are 3 kernels, right? Because there are 3 kernels. Okay, very good. Now, to compute the value of this unit, this specific unit, not all of the 3, okay? This one, we know that it's a kernel size of 3, right? So it will be applied to these 3 values from the input. So the receptive field, the field of sight of that hidden unit is these 3 values. Okay, which means only these 3 values affect the value of this unit. Okay, type. How about this one? Same. Why is this the same? Why? Different kernel. It's different kernel, but applied at the same region. Okay, different kernel, but it's applied at the same region, and the same, of course, for this. Okay, type. Now let's add another layer. Now, how do you interpret these numbers? How many channels we have here? 4. How many channels we have here? 3. So 3 by 4 by 3. What is that 3? The kernel size. So this is the weight matrix. Okay. So the weight matrix has all the weights. Okay. So this is the kernel size. Type. Now, what's that? Yeah, but this is K. It's 3 by 3. Okay. It's 3 by 3 because of the number of input channels. So that's the 3 by 3. No. We in the terminology we say its kernel size is 3. It has to be square. We don't say the kernel size is 3 by 3. 3 by 3 is different. No. It's the kernel size here is 3, but it's applied to multiple channels. They are different. But when we say the size of the kernel, we mean the size of the region in each channel. In one channel, which is 3. So the kernel size here is 3. Okay? Huh? Okay. So let me. The kernel, okay? It's 3 weights, okay, for this channel, and then 3 other weights for the second channel, and 3 other weights. No. Okay, the terminology is it's the terminology. The terminology is the size of the region for one channel. Okay, it's applied to multiple channels. So we have 9 weights here, but the size of the kernel is 3. That's by definition. That's just a definition. Okay. Sorry. Why is it what? Why we have 4 output channels? We have 4. So this kernel is producing this channel. This channel, this other channel, is produced by the second kernel. That's by the third. That's by the fourth. Okay. Yeah. Oh no, no. Size is 3 because we have 3 input channels. No, no. Even if we have 10 input channels here, still the size of the kernel is 3. But now the number of weights will be 3 times 10. Okay. Let me erase all of that because we don't need it now. Okay. Now, so you understand now the numbers, right? How about the receptive field? The receptive field. Let's take this unit. This unit is computed over which values in the previous layer? The 9 values here, right? Because it's applied on all of them, right? These 9 are computed over which region in the original input. So the receptive field is about the original input, the very first input. What is the receptive field now? You would see that these 3 are, now I think it's better to use the pen. These three, yes, are affected by these. These 3 are affected by these. These 3 are computed over these. So this one is computed over all of these 5. Okay, so the receptive field of this one is all of these 5. Okay, you got it now? The brown ones. That's exactly what we have here. Okay, is that clear now? What do you notice now? With adding more layers, what happens to the receptive field? Increases. That makes sense, right? Because we are now convoluting regions that were processing smaller regions in the input. So it's like we are integrating information across layers, right? So first we got information from smaller regions, then these smaller regions are combined, okay, into the second layer. Then larger regions will be combined for the next one. So the receptive field, if we add one layer now more, you'll see that the receptive field increases. Okay, now each of these units is computed over that region in the second hidden layer, which are computed over that region of the first hidden layer, which are computed over that region over the original input. So where is the receptive field of these? This. Okay, in the original input. The brown ones in the original input. That's the receptive field. Okay, as we add more layers, the receptive field, the receptive site, okay, of the nodes in the hidden layers will increase, right? Because they are computed over now larger regions. Okay, and that means that the information is integrated. Okay, first the information was about very small regions in not the image yet in the input. Then they are combined, so the receptive field decreases a little bit. Then they are combined, the receptive field decreases and increases, and until at some point we might cover the entire input. Okay, as you can see here. Okay, so that means that here in that specific case, all of these units now are computed, or have covered, or have seen the entire input. Okay, and the intuition here is that the first layer, because it's applied on a very small receptive field, so it will try to learn patterns on small regions. Like مثلا, if we are talking about images for a second, like edges in the image. And then the second layer will combine these edges into maybe a frame figure, okay, and then into an object, and then into a complete scene, and so on. Okay, so every layer has a higher semantic role as we add more layers. Okay, is that clear? Okay. Now let's see an example, a real example, okay, of a convolutional network. You saw this data set before, right? The data set of the digits. And remember that we converted, these are originally images, but we converted them into 1D. It's just 40 feature values. It's like one vector of 40 values. Okay, so now we can process it by 1D convolution, by what we studied already. Okay, type. There is an experiment on that has been done using convolutional network. Here is the description of the network. We have, of course, 40D input because we have 40 features. We have 10D output. If you remember, what was the task here? Recognize the original digit, right? From 0 to 9. So we have 10 possible digits. So the output eventually is 10. Okay, so that's the event. The output layer of the network, of whatever network we design now, has to be 10, because if you remember multi-class classification, we have to have 10, and then we have softmax to get the probabilities. You'll see that. So there will be a softmax at the end. The structure of the network has 4 hidden layers. 3 of them are convolutional layers, and the 4th is fully connected layer. Can we do that? Yes, of course, you can. It's just the mathematical functions, right? You can stack whatever layers you want. You'll see how the structure will look like now. The total number of parameters for this network is 2050. And that network was trained for 100,000 steps with SGD. What is SGD? Stochastic gradient descent. What is LR? Learning rate. And the batch size of 100. And the total number of training examples in this case was 4,000. Let's look at the network. This is the network. Okay, let's try to understand everything on that figure. First of all, the input layer, how many nodes we have here in the input layer? 40, because we have 40 features, right? So that's 40. Okay, then we have a convolution layer. No, don't look at the numbers and the text. Look at this figure. So this is like the hidden units in the layer. This is a convolutional layer, and it's structured that way so that we know how many channels. So how many output channels in this layer? The number of columns here, right? Okay, which is 15, and the number of rows here is 19, which means what? Which means that from the size of 40, it shrinks to 19, which means that we are doing a convolution with a stride that is not 0. That's not 1, right? It's probably 2. Stride of 2 will actually will get half of the size. Okay, so you will see that stride is 2 here. The number of channels is 15. We said that, and the size of the of the kernel is 3. Can we actually tell the size of the kernel from this? No, the size of the kernel, not the number of channels. Can we, from the number of hidden units here, can we tell the kernel size? From, even if you know the stride. No, we cannot tell. Okay, so it's the size is 3 here, so we cannot tell actually from that figure only. Okay, but the size here is 3. Okay, so that explains these numbers, right? One is one input channel, 15 output channel, and that's the size of the kernel. Okay, and the number of biases is 15 because we have 15, and we have 15 output channels because we have 15 kernels. Very good. Okay, now that's the first layer. Second layer, similarly, we have 15 channels, 9 hidden units in each channel, which means that we have a stride of 2. We were 19, now it's 9, almost half. Okay, so we have a stride of 2, and again the size is 3. Okay, That's the second layer. Third layer, 15 channel again, 4, which means again we have a slide of 2, and the size is 3. Okay? Now, how many hidden units we have overall here? Which is 60. Okay, 60. Now, the fourth hidden layer is a fully connected hidden layer, like the ones that we discussed earlier. Right. A fully connected layer has to have the input to be 1D. It doesn't understand the channels and all of that, right? It's just 1D. So we have to convert this 60 units into a vector, just represent them into a vector. Okay, just a representation. We will not change the values. We just stack them in one vector. Okay, so that will be 60. And the hidden, actually it's not the hidden layer, but it's the output layer. Will have how many nodes we said? No, the output. 10. Okay, so between the output that is 10 and the last convolution layer that is 60, we will have a fully connected layer. Okay, so we'll have 600 weights between just for this one fully connected layer, and then the softmax. Okay, that's why you have 10 times 60 here, right? 10 is the output nodes, 60 is the input nodes of that fully connected layer. Okay, so I think you understand every single number on this slide now, right? Yes. The input to that layer is 60 because we said that we will represent this in one vector. It's not the original. Original is 40. It's the output now, yes. It's just one, we added one output layer here. Yeah. You can consider it hidden if you think of softmax as another layer, but actually softmax is just an activation function of it. Yeah, so you can consider it as the output layer here. Yeah. So if I ask you to compute the total number of parameters, I think you can do it, right, for this. So you have to do that exercise and make sure that you will get that number. Okay? Not now, of course. Okay, right. Now we will compare that with a fully connected network of the same size of the convolution layers. So this has 19 times 15 hidden units, right? So we will have a hidden layer with that size, another hidden layer of that size, of course, 1D, and another hidden layer for that size. Okay, and the total will be 59,000 parameters versus 2,000. Okay, so a huge reduction in parameters, of course, because they are shared, right? Because they are shared. Now we will compare the performance between the convolutional layer, the convolutional network, and the fully connected network. Which one you think will produce better performance? What? The fully connected. Why? Because it has more parameters, right? It's so the information sharing is a good thing, right? So you mean so your convolution will be better, or the fully connected one will be better? Okay, let's see. Let's see. Okay, let's see. Okay, so on the left, this is the convolutional network, 2050 parameters. On the right, the fully connected network, the 59,000 parameters. And what do you see? Which one is better? This is error. Okay, so the performance measure here is error. So low values are better. Okay, converge faster in training, but in test, I mean this converged faster in training, but in test the error was really high. Okay, what happened with the convolutional network? The error is less. Okay, so it has a much better. Actually, I think maybe the error here is like 50% of that error. I think something like that. Okay, so reduced the error extensively or significantly. But why is that?
in the vector, each number depends on the ones before it. So sharing the weights really helps in recognizing.
Sharing the weights, and also the fact that we are producing local regions. So this is coming from an image, although it's 1D, but it's coming from an image. Okay, it's conversion or transformation from an image. So the local processing is very important. Okay, and for the fully network to learn the patterns that we will learn from the kernels, it has to be learned over all the parameters. Okay, with different regions, from different regions, or for each region separately actually. But the convolutional network, because it has what we call the inductive bias, that each position should be, each region in the image should be processed in the same way, it was able to find solutions that are much better. So the intuition here is that we have a better inductive bias. The inductive bias, which is about the structure and the design and the assumption of the convolutional network, forces the network to process each location similarly, share the information, and the search across much smaller parameter space. And if you think about it, the number of parameters here is 2,000 versus 59,000. The number of solutions in fully connected network is huge. Okay, to search within that very large search space, much harder to find good solutions than searching within much smaller space. Okay. Type, yes. Good. Probably what happened here is overfitting, because we have very large number of parameters. Okay, but it didn't generalize. Probably this is the case, but it didn't happen here. Okay? It happened, but very, very late, after many training steps, but happened much faster here because of the number of parameters. Well, we have lots of parameters. Okay. So the generalization for the convolutional network was much better. Was much better, which means that if you remember the discussion of the double descent, the interpolation between the data points is much better in the case of the convolutional network. Okay, now we will extend what we have discussed from 1D to 2D. Okay, just one quick comment before we extend it to 2D, and you will see that it is really simple. One comment: with 1D, without extending it to 2D, do you think it is useful? Can we process actually input with 1D convolutions? 1D convolution means that the input is 1D, is just one, each channel is 1D. Okay, can that be useful? And we saw an example and it was useful, but that was from images originally. Can we process something that's not image and by CNNs?
You can. I have an idea, but I want to ask.
Can we process text?
Yeah.
Why not? If each of the hidden unit you expanded to an embedding vector and you put them all in one vector, that's text, right? And even the idea of processing small regions makes sense also in text, right? Words that are close to each other they have relationships, right? Probably the idea of attention in transformers is better, but this came before that, and CNNs actually used for processing text in reality. Audio can be processed also because it's 1D signal, right? So audio also can and any 1D sequence of input can be processed with 1D CNNs. Now to 2D convolutions, the idea is now the kernel itself will be a 2D object. So in 1D convolution, the kernel was 1D, but applied in depth. Okay. Now the kernel itself, because the input channel will be 2D, the kernel itself will be 2D. No, it wasn't. It wasn't. It was 1D, but has a depth over the different channels. If we have one input channel only, it will be just one vector. Right?
Is it going to be like this?
Huh? Let's look. Let's see. So this is, we will see it in the next slide. Okay. But so far it was just 1D. Yes, it's one vector, but has a depth. Okay. Now, because the input was 1D, the one channel, and all the channels that we saw before, the input channels were 1D, right? Even the output channel was 1D. Now, the input channels themselves, each will be a 2D channel. 2D values. The values will be in 2D. Okay? It will be a matrix, yes. And now the kernel, instead of moving in one dimension, it will move in 2 dimensions, horizontally and vertically. Okay? The equation is very similar. Instead of applying it to one dimension, it will have double sums because we have 2 dimensions, right? Okay. Horizontal and vertical. And again, adding one bias and applying the activation function. So similar. Let's see an example here. This is one channel, one input channel, but it's 2D now, right? How is that different? The only difference is that the kernel itself will be 2D. That's it. Done. Okay. Weighted sum, again, it's a weighted sum over a 2D region. And then it will be shifted across the entire region. Now, instead of producing a channel that is 1D, now the output channel will be 2D. That's the output channel, right? Because we are moving the kernel in 2D, right? So for processing this region, this kernel will produce this value. Let me change to the laser pointer. So processing this region with this kernel will produce just one value, which is this one. If we shift it to the right and down, this is another region, will produce another hidden unit. Okay, doing it over the entire input channel will produce one output channel. Yes. We'll see. Similar concept. Though. What do you expect? If we have 2 input channels, what will be the difference? The depth. The depth. Okay, same thing, but it will have a depth now. Okay, so it will be 3 by 3 by the number of input channels. Okay, that's a third step. Now we will also have zero padding or whatever what we will do with the corner cases. Okay, so here we'll have zero padding. Here also we have zero padding, right? Same thing like what we did in 1D, but now it's in 2D. Okay, any questions so far? So this is the same concept, except that the kernel now is 2D. If you understand very well what we have, what happened in 1D, very easy to be extended here with 2D. Type. What if we want to have multiple output channels? Multiple kernels. And all of the kernels, of course, will be 2D, right? So we'll have multiple output channels. Now this is the real application. Now the input is an image. Okay? And the image by structure, by definition, has RGB, right? Channels. Each of these red channel, green channel, blue channel. So the input, someone asking me about what if the input has multiple channels, right? that's the case. So the input itself, so this image actually has 3 channels. The red, green, and blue channels. Now, applying this kernel, why do you have now, the kernel now is 3 by 3, okay? So why do you have all of these weights for the kernel? Because it's 3 by 3 with a depth 3, because we have 3 input channels. Okay, so the kernel now has how many weights? 3 by 3 because it's a 2D, and because we have 3 input channels, it's 9 times 3, 27. And all of that will be applied to that region. So this is like taking a part of the image. Okay, so this is that part across the 3 input channels. These weights will be multiplied by these values, producing one hidden unit in one specific output channel. Can we have multiple output channels? Yes. Different kernels, same concept. Okay, now you see it as for images. Now you start to see it for images. Yes. Channels also, but maybe different meanings. No. The number of channels of the output, we control it because we design or we set the number of kernels. But then the input channels, they come from the input. Depends on the input. Okay. Okay. One more slide, or that's it? Just one more slide. Okay, one more slide. How many parameters? I think it's easy. How many parameters? If we have CI input channels and the kernel size k by k, now the size is k by k. Okay, it's not k. It's k by k. And now you understand why. Okay, so the size is k by k. Then the weights will be k by k times CI, right? Because we have the depth. Okay, and the number, the biases for one kernel is 1. This is for one kernel, by the way. Okay. One bias, weighted sum plus bias. Okay. Now, if we have CI input channels and C out output channels, times C out. Okay. So CI by K by K times C out, and the number of biases are C out. Why? No. The number of kernels. The number of kernels are C out because each kernel will produce one output channel. Okay. Nice? Okay. Inshallah, we'll continue next time. Assalamu alaikum wa rahmatullahi wa barakatuh.